Hi everyone. Today we are here to present our paper on Select and Optimize, which is a novel proposed deep learning-based method aims to solve large-scale TSP instances. In this presentation, we are going to discuss current research on learning-based combinatorial optimization, especially on TSP problems. We are going to give a detailed description of our proposed method in this paper, as well as the experimental result from our research. This presentation is mainly divided into four parts. First, let's begin with the background of our paper. In this part, we are going to review the combinatorial problem and the traveling salesman problem. Then we moved on to the learning-based methods with a short review and summary. Finally, we are going to show some motivations and contributions of our work. The SAIL problem aims to find the optimal solution under certain constraints, and the TSP is a typical NP-hard problem in this community. TSP seeks to find the shortest possible route that visits a set of given cities and returns to the beginning point, as we can see in this figure. There are plenty of applications based on TSP problem, such as the logistics, delivery, and so on. The main challenge of solving TSP problem is how can we find a near optimal solution within limited time. In other words, what we want is to find a solution that is close to optimal while also being efficient enough in time consuming. Compared to conventional heuristic methods, deep learning-based methods provides a more efficient and effective way. Learning-based methods can be roughly divided into supervised learning and reinforcement learning. There have been lots of works on these two fields. In supervised learning, pointer network is the first to deal with TSP problem. It is a sequence-to-sequence model with a decoder to construct the solution step by step. The following research also use graph networks to formulate the embeddings of TSP nodes. Unfortunately, supervised learning needs optimal solution labels in their training procedure, which is expensive to get and sometimes even unavailable. Thus, reinforcement learning-based methods are getting popular recently. A typical method is the attention model proposed in 2019, based on reinforce algorithm. However, it is difficult to apply these methods to large-scale problem solving. So, as a meanwhile, some recent works focus on this problem, mainly include end-to-end learning and improvement-based learning. Attention GCRN MCTS is a typical method proposed in III 2022, which it is also the first learning-based method solving 10,000 size TSP problems with faster speed and competitive performance compared to heuristic methods. Another method, also an interesting work, the neural LCage. It is a typical improvement-based method. It combines deep learning with LCage3, which is the commonly used heuristic solver. With this research, there are still some challenges to be addressed, especially in large-scale TSP problems. The labels of these problems are difficult to get in supervised learning, and it is also difficult to train a policy to directly deal with these problems. Besides, the time consuming in most research are still too high. So the motivation of our paper is to find an efficient solution to large-scale TSP problem, following the divide and conquer idea. Our contribution in this paper can be summarized as follows. We introduce a novel framework called Select and Optimize to apply small-scale solver to large-scale problems. In the sub-problem solver, we adopt the transformer-style encoder-decoder architecture to get better sub-solutions. Also, to avoid the local optima, we introduce an operator called destroy and repair to improve the global solution quality. In the following part, we are going to introduce our method in details. Okay, let's move on to the second part. In this part, we are going to introduce a framework, select and optimize, the subsolver design, as well as the destroy and repair operator. The main framework is shown in this slide. At the beginning, an initial solution is constructed. At each step, subproblems are sampled in batch, as we can see here, these subpasses. And then these subpasses are fed into the subsolver network. We call it neural selector and optimizer. After that, the most promising sub-solution, XS, is selected and transformed into a new global solution X prime. The destroy and repair operator is applied in this solution at a certain updating interval. This whole procedure will be repeated several times until the final solution cannot be improved. There are two essential steps in this framework. The first is the subsolver neural selector and optimizer. It is built upon transformer architecture. In the encoder network, all of the node location xi is projected into an embedding space with L stacked attention layers. These embeddings are denoted as hi with superscript L. The decoder is then applied to generate the logics of candidate nodes. We use a multi-head attention layer to generate the query vector and a single head attention layer to compute the logics. As we can see here, the query vector is calculated on the context embedding HC superscript L. This context embedding is a concat of 3 embeddings, corresponding to the node embedding visited in the last step, the head node embedding and the tail node embedding. In fact, we find the tail node embedding is very helpful. We use policy gradient technique to build our loss function gradient. Rpi is a negative tool length, and the baseline function is the average batch rewards. Here we use another trick. As we know that the subproblem is symmetric, thus the decoding process is conducted from both directions, from the start to the end, and also from the end to the start. In the experiments, we found this trick also helpful. The second essential step of our framework is the destroy and repair operator. In our early experiments, we found some bad cases. There always have been nodes with long distance but connected together. We call this as bad long connection cases. Here is an example in TSP 2000. We introduced an operator called destroy and repair to handle them. Here it goes. Once the solution is generated, we will destroy the longest connection to segment the global solution into pieces, and then repair them into a new solution using LKH method. This operator is very simple but quite effective to break local optima. We test our method on generated dataset as well as a real-world dataset. Here is our results. We construct two subsolvers named SO50 and SO100 according to different subpath lengths. Also, we use a mix form. In our paper, we call it hours mixed to re-optimize the solution using SO50 after SO100. We test our methods on different scale TSP problems, compared with both conventional heuristic solvers and learning-based SOTA methods. From this table, we can see that the performance of our methods is better than learning-based SOTA, especially on TSP 10,000. And the solving time of our methods is shorter than half of conventional methods. Here we want to say that we don't aim to strictly outperform conventional methods, but the gap can be further reduced with more inference time. We also test our methods on real-world dataset from TSP Lab. TSP Lab is a library of samples instances from various sources and types. We divided the large-scale instances into two groups. From the table, you can see that our method offers 6 times and 25 times speed up while achieving competitive solution qualities. The right table is a detailed result on each sample. We can see that our method is much more stable than a learning-based sorter. There are some ablation experiments listed here. We test our subsolver with or without two-node embedding, with or without symmetry. The conclusion is that with two-node embedding and symmetry, our subsolver can perform better. Also, with the destroy and repair operator, our method is significantly improved. Here is another experiment on TSP 20,000. As far as we know, we are the first learning-based method solving this scale TSP problem. Our method is 2 times faster than LKH3. Finally, we come to the last part of this presentation, the conclusion. To summarize our paper, our proposed select and optimize framework could significantly reduce the computation loss cost while improve the solution quality in TSP problem solving. Concretely, the experimental results show that our methods can produce competitive solutions with less than half of the runtime compared with learning-based sorter. But there are still some questions that need to be answered in the future work. The first is, in many real-world scenarios, they have different constraints. The data distribution is also different from the generated data samples. And there are many other large-scale CO problems, such as the VRP and bin packing problem. Also, the local optima is a big question. Maybe we can turn to other techniques to alleviate, such as the evolution strategy, combined with learning-based methods. This is our presentation. Thanks for your listening. If you have any questions or concerns, please contact us.